Good day, I am Paul Ang from Sarai Project 2.6 Drought and Crop Assessment and Forecasting or DCAF. I'll be talking about our preliminary study on drought forecasts, specifically for the past 2018 to 2019 weak El Nino. Drought occurs in the country every few years, typically when there is an ongoing El Nino, here shown as dips in rice production. From late 2018 up to mid-2019, there was a prolonged weak El Nino, which resulted in nearly 8 billion pesos in crop damages by April 2019. It is thus crucial that we are able to forecast drought, especially during El Nino years, so that we can be proactive in mitigating the impacts on the agricultural sector. Institutions around the world provide readily available global forecasts up to 6 months in advance. But since our country is an archipelago, we have to increase the spatial resolution of these forecasts in order to capture our complex terrain better and provide regional level warnings. One method of increasing the spatial resolution is called dynamical downscaling, which makes use of the global forecasts to generate realistic forecasts at the regional level using advanced climate models. However, forecasts have errors which may be due to the inherent uncertainty of the future. The time interval between the time when the forecast is issued and a certain time in the forecast is called the lead time, and generally speaking, the error increases for longer lead times. The climate models may not accurately simulate the local weather patterns, hence forecasts may be better or worse depending on the location or the season of the year. Hence, in this study, we demonstrate the potential of using dynamically downscaled forecasts from 0 to 5 months lead time by evaluating their performance during the weak El Nino last December 2018 to May 2019 for the Philippines. We investigate the forecasts for 3 drought indicators, namely rainfall, land surface temperature, and surface soil moisture. We use global forecasts from the Climate Forecast System version 2 or CFS v2 at 100 km spatial resolution, then increase the resolution to 25 km using the Regional Climate Model version 4 or REDCM4. We use sensors from satellites to evaluate the forecasts, particularly the Global Precipitation Measurement or GPM for rainfall, the Moderate Resolution Imaging Spectroradiometer or MODIS for the land surface temperature, and the Gravity Recovery and Climate Experiment Follow-on or GRACE-FO for the soil moisture. We downloaded a set of 20 global forecasts from CFS v2 for each starting month from June 2018 to April 2019. Each forecast was downscaled with REDCM4, then averaged for each month for rainfall and land surface temperature. For soil moisture, we computed the maximum soil moisture percentiles or the soil moisture relative to the past conditions of 2001 to 2010, which is the longest period we have been able to simulate as of now. Then we group the forecasts according to the lead time for each target month. For example, the first diagonal line in blue are the 20 forecasts starting in June 2018, which have starting dates from June 1 to June 25. Thus, the earliest the June forecasts can be released to the public is less than a week from July. So for the forecasts starting in June 2018, there is only a 0-month lead time for July 2018, 1-month lead time for August 2018, and so on. We got the forecasts with lead times from 0 to 5 months for December 2018 to May 2019, as shown by the dotted columns. In comparing the observations and forecasts, we used box plots, standard deviation, and monthly maps, which I will all explain along the way. The box plots were used to compare the range of values across the country for each variable and month. Hence, we can infer the general seasonal variability from box plots. We have the rainfall box plots from the observations, lead 0, and lead 1-month forecasts, which all peaked during December, then died down during the dry season and recovered in May. Temperature forecasts, on the other hand, are evidently colder, missing the extent of the El Nino surface warming, but still increased slightly by March. The wettest conditions from the soil moisture values are only close to the observed during December and May for lead 0. The rest of the months have wetter soils. This may be due to the short 10-year reference period as compared to using the standard 30-year period for climatological studies. This leads to values that are either extremely high or extremely low. Now we compare the standard deviation, which we use to measure how different are the forecasts using different lead times. We normally expect forecasts to perform worse for longer lead times, but if the standard deviation is low, then the performance is consistent. Rainfall and temperature showed relatively low standard deviation throughout the country for February and March, while the rest of the months have a larger spread for certain parts of the country. For soil moisture, the standard deviation is low for December, while the rest of the months have higher values. This may be due again to the short reference period used, which tends to give a larger spread. Comparing the monthly maps between the observations and forecasts revealed which areas of the country did the forecast perform good or bad. Here we have the monthly maps for rainfall and the forecast for lead 0 and lead 1 month. The effect of the northeast monsoon is seen in the observed maps for December and January, where the forecast showed heavy but less intense rainfall. The dry conditions for February and April were generally captured. For the forecasts, the months of December, February, March, and April were relatively consistent. For temperature, it is apparent that the forecasts hardly change across lead time, but this may be because the difference between the observed temperature and the forecasted temperature is larger than the changes across lead time. This error may possibly be reduced by changing the model settings when the global forecasts are downscaled. The cooler climate may have resulted from the current model settings, or it may be inherent with the inputted global forecasts from CFS v2. As for detecting drought through the soil moisture maps, we focus on whether the low moisture areas in the red and orange colors were reproduced. The forecast captured the January dry conditions in Mindanao, as well as in central Luzon from February to March. The April drought signals were too intense for northern Luzon and Mindanao, while hardly any drought events for southern Luzon and Visayas were forecasted. For the summary and conclusions, the potential of dynamically downscaled forecasts was demonstrated with the 2018 to 2019 weak El Niño. Lead time persistence was observed, but only for select months. Rainfall forecasts performed the best, capturing the seasonal variability and general spatial patterns, whereas temperature forecasts were consistently colder for all months. Even though soil moisture forecasts were wetter overall, they were still able to produce several drought-affected areas. For the recommendations, bias correcting the forecasts may improve the results in the short term, but it is more recommended to fine-tune the model settings or test other global forecasts as well. Once we are able to simulate the 30-year reference period, the results for soil moisture percentiles should improve. Or, alternatively, we can use soil moisture percentages instead from satellite-derived datasets. Lastly, in order to get a better picture of the overall performance of the forecasts for operationalization, other seasons and years should be considered as well. We would like to thank the DOST ASTI Corps for the computing facility, as well as the DOST Picard Great Assistantship for making this presentation possible. Here are our references. Thank you for listening.